Hello everyone. So today we will see a typical question: why there are databases optimized by writing data, and there are other one that is optimized by reading. It's like when you compare Cassandra DB versus PostgreSQL, and this is not related nothing about NoSQL versus SQL databases. Okay, so in the last video I explaining why actually long structure merge tree is optimized by writing. In this case, we will focus on B-Tree, but I will promise you that in this video I will explain you to understand how it's working B-Tree, and it will be easier to understand why we have this difference of optimization on the database. We can see in this overview that in the left side we can see the logic of the B-Tree, and the right side the LSM-Tree algorithm. Okay, this video coming from the video series talking about the same data intensive application book. This is the 2026 edition. Thank you again for watching this video, and we can start it. So the first thing, we can summarize everything if we can explain how it's working long structure. Okay, so long structure is very is optimized by writing because we have a pen only. Okay, if you have any change that you want to do in the storage, it's like an append. It's like if you want to update a key value, it will generate a new log, right? That of that change, and it will be immutable. It's like if you generate any change that you wanted in this key, it will generate a new row, a new log in this file to register all the change that you have in this storage. And with this file, with all the changes generated, it will generate a segment that is files that have multiple versions of the key value that finally you have to find when you trying to read data, uh, in which segment is the latest version of the key. And in the case of the B-tree, is composed with in place. It's like when you want to or update a value, you have to overwrite it. The value that you already have in the database is like, for example, if you want to update a some key, you have to first find in which place is located this key, and finally overwrite the value. But it's like there is not an append log that you insert something. It's like if you insert something, you need to sort in everything, and finally insert this new key value. Okay, obviously, with this explanation you can see that okay, it will be faster if you reading data because you are working with sorting data, and if you need to write in something, you need to first find it and then overwrite it. So that is in super summary. Okay, but we will deep more. The B-tree is composed with a page-based architecture. Okay, in this case, we can see this comparing. In the LSM tree is composed with segments. Okay, segment is the place that is located the key value with multiple versions, right? Because you need to find in which version, in which segment you can find the latest version of the key, because that segment could have a tombstone, right? Remember that. I explained it before everything in the latest video, but I'm trying to do a summary, okay? And if you want to find a key value in this segments file, you have to use the Bloom filter. But the Bloom filter have the penalty that is not confident to know that if you want to find a key, you don't know actually if in this segment it will be located the latest version. You have to filter in multiple segments using the Bloom filter, right? The unique thing that you could have the confidence is that if the Bloom filter said that the value is not there in this segment, you can know that is 100% that is not there, but only that. Okay, the rest of that is located that is like it's probably to be there or not. That's all. But in the case of the page-based architecture, it's composed with multiple pages, like we see here in the button databases, right? And everything is sorted. So if you want to find something, you only need to check a range of indexes and find it in which page it could be located the value that you want to find. So it will be faster to read something, but it will be complicated if you need to write in something, because you need to sort it again, balancing again. Okay, so that is the problem. Okay, and the size of of each page, it will be depend for the all the database storage that you wanted, you are using. You can use Postgres or MySQL. It will be a different size of the page. Okay, in this video I don't want to talking about a specific database because actually there are multiple alternatives. We're talking about only the algorithm, internal algorithm. Okay, because actually MongoDB is using B-Tree. Okay, so okay, again. So we can see what is the B-tree structure. In this case, we can see the balanced hierarchy, right? And it will start with the top place. That in this case, it will be the root page that is composed with multiple ranges. And you can find in these ranges in which level, in which page you can find the possibility to find the key that you wanted. Okay, it's optimized by reading. So first you start with the root page, then you have to find the internal page you wanted, and finally you can find the leaf page. It's not necessary to have only three levels. Actually, it's an example, but that is the idea. It will be better if you can see an example. So we can see in this diagram. Okay, started with that you want to find the user ID 251. Okay, imagine that you want to find that. So first you want to you have the root page. The root page is composed with multiple index that is sorted. So in this case we have the 100, 200, 300, 400, and 500. So you have to know that the you have to find that which range it will be stored your user ID. So in this case you can see that it will be between 200 and 300, okay? Because that is the value that it will fit there, right? Everything is sorted. So in the second level, if you want to do the internal page B, you can see that you have to do the same logic, okay? So you have to find which range it will be included this user ID, and in this case, it will be between 250 and 270, okay? So if you deep more in the next level, you will see, okay, the leaf page, that it will be located a value. And finally, the thing that you want to overwrite it or you want to read something, right? So in this case, you can find the user ID and that's cool, okay? But that is only to read in something, okay? The problem it will be coming when you want to write in something like an insert or delete, okay? We can see in this example, okay? Imagine that you have to this parent page. You have the parent of the 40, right? And 40 have a leaf page that have a three three reference here of key. Okay, we have 10, 20, and 30. Take a note that the branching, when they are talking about branching size, in this case is the number of the keys or reference of page that could have a page level. So in this case, take a note that you want to insert 25 in this page, right? Obviously, you located that it will be have to place it in this leaf page because it's in this 40 40 range, right? And there will be a max capacity or branch capacity of three keys. So in this case, there is no way to include it in this leaf page. So the solution is that you have to promote this leaf page and split it to generate two leaf page. So we will have the left page, left leaf, and the right leaf, right? So you can finally know that, okay, this 25 key it will be located in the right leaf. And it will be updated the parent page because you will have to store it the left leaf and it will be in the in another reference, right? So that's it. And that is in the case of you want to insert, that it will generate a balancing or rebalancing in this case, okay? And the problem it will be coming if you want to delete. In this example, you imagine that you want to delete the 10 key, that is in the case of the left leaf, right? And take a note that there is no way that you can have a leaf empty. So that will become a problem because if you want to delete it, you need to merge the right leaf, taking a note that the branching side that I explained to you is that you have to support three keys, right? So in this case, you will remove the 10, right? And you will try to create the leaf page to have that three keys that I tell you when I tell you that we have a capacity of the branching of three keys. So you will demote the 20 that you have on the parent page, and then it will become a leaf page because you need to have the capacity of 3. So in this case, it will be affected the parent page and the leaf page if you want to delete it. So in both cases, it will generate a rebalancing, and that rebalancing it will generate it will be generate a latency. Imagine that you want to crash recovery, right, or durability, because obviously when it's generating or this process this B-tree to update the insert and delete keys, you need to confident that if you database is down, when it's recovered, everything it will be restarted and generate again the B-tree according to the logic that we have, right? So in this case, we will have an write ahead log, like an append log that we have an LSM tree. But in this case, we will have another purpose. The purpose of the writing ahead log in this case of B-tree is only to keep the data or persist the data to recover at the moment that the database is down. So the first thing it will be generate this change of the storage. It will generate an append log, right, to persist the data. And when it's in a great ahead log, you can know that okay, it will be confident that storage it will be consistent later, right? So that's it, the logic. And we can see the read mechanisms of both algorithms of storage. Okay, so if we can see the bit read, we can see that the logic will be faster because you only need to deep in multiple levels, and you will very sure that it will be the value in some leaf page. But in the case of the LSM to read, the problem is it will be with the Bloom filter. Maybe if the value it will be in the mem table, obviously it will be fastest. But in this case, if not, is missed there because the key is very old. Obviously, it will be in the segment, but in very low level, right? So you need to go to the segment and need to be filtered by the Bloom filter, and that it will generate a latency. And for that reason, the read mechanism it will be better for B-tree, right? And in the case of the write amplification, it's the same thing. The problem is that in the B-tree, you need to rebalance in multiple places, depending of the chain. First, you need to find it the key value, right? That you know that it's fast. And obviously, if you updated something, it will be fast. But if you generate an insert or delete, it will be expensive. But in the case of the LSM-tree, it will be fast because it's only an append log and it will be updated on the MM table, and that's all. So it will be faster. So here we will have a summary of everything, right? To very, very clear that which is the difference. In the case of the operation, obviously, it will be a different reason to be implemented B-tree. If you have an read heavy requirement, it will be decided to use the B-tree. And in the case of the write heavy, it will be LSM-tree, right? The data structure it will be different. We are talking about page-based or segment-based, right? And the update model it will be in place when we're talking about B-tree and append only, like I said in LSM-tree. And IO pattern it will be different because it will be random in B-tree because you don't know in which places you need to update it. You need to locate the first page. But in the case of LSM-tree, it's sequential because always you need to only add something in the same page, in the same in the latest log, right? So that's all. In the read speed, it will be faster on the B-tree, and in the greatest speed, it will be faster in the LSM-tree. And the application is like I said you before. Obviously, B-Tree will generate an graph application very heavy, right? Because we have an rebalancing, and the LSM-tree not. Everything will be stored in the MM table on the segment, and the parameter will be on the read. So that's all. So in this case, we will see. In summary, what is the difference? I hope that maybe you can understand and learn how is the difference. And no, I'm not talking about nothing of CQL versus no CQL. Thank you for watching this video.